Okay, thank you everyone for sticking around after lunch. Okay, so Neil gave an excellent talk, and Lavanya told you to do UVM and test benches, and I'm now going to tell you to not do any UVM, don't do any test case generation, forget everything you have ever learned about test generation, and do formal. Because formal is the new normal. And well, it's not quite yet the new normal. We are trying to make it normal. So I started Aximize 5 years ago, a little over 5 years ago. And my son, who's sitting here, is one of the person who was involved from the very starting stage of the company. And the slide deck is also made by him. So if something doesn't work, you know who to blame. He's sitting here. Okay, so the idea here is to make formal so cool and normal and easy to adopt so everybody can actually benefit from what it is in terms of technology, what it is in terms of methodology, and therefore there are no corner case bugs left for you, last minute surprises, respins. Um, so that is the vision anyways, and that was the dream in 2017. So we have been doing quite well with our vision, and we have been driving a lot of these different strands. So we started focusing on training and enablement, which is still a theme that I'm quite passionate about. So I teach people in instructor-led courses, and there is an on-demand course called FE 101, which you can take in your own time. Consulting and services is the core of our business, which is where we are spending 99% of our time. And apps is an area which we've been very passionate, especially because of RISC-V. So RISC-V has brought the world together, and it is making great strides in open source architecture and design, and in verification, as we heard from Neil's talk and Lavanya's talk. A lot of cool stuff is happening. We are driving a lot of RISC-V work in formal space, and we're making it cool by actually making it super easy for you to use. So consulting and services, as I said, is our core work, and RISC-V is part of our business. It's not entirely everything that we do. So when we are not doing RISC-V, we have been looking at designs with over 1 billion gates in compiled footprint, and we've been doing functional verification on those designs. The reason we are able to do this is because we have abstraction-powered methodologies, which can actually go very deep in the design space and can figure out if there is a bug or not. So if you're doing an AI ML accelerator, if you're doing a NOC, Ethernet switch, mixed signal low power chip, power controllers, DMA controllers, multi-threaded processors, bus bridges, cache subsystems, GPU blocks, or any of the SoC peripherals, Formal is very much ready to find the bugs and prove that the bugs don't exist. That's the one of the main benefits of Formal. So the number of customers we work with, unfortunately, they have not allowed me to tell you who they are. That takes a lot longer than finding bugs. So one customer we were working very closely in the last couple of years. A lot of interesting excitement, test and simulation is the de facto verification paradigm. So people who are new to Formal always take time to get used to what we are trying to do. After the project got finished, he turns around and says, nobody should ever do chip design without Formal. And basically, one customer said, when problems get hard, they come to us. I love the fact that they only come to us when problems are really hard. It also gives us a lot of juicy challenge to look at. So we've been busy driving a lot of consulting and services work. And if you wanted to look at what some of the customers think about training, it's also online. So enough of marketing and PR. Let's talk about verification. So what happens when we get it wrong? So I have to pay homage to Intel. I continue to do this. I started my career working with Intel many years ago as an intern. But I think everybody here knows about the famous FTIF bug in mid-90s, and Intel had to replace every single Pentium in the world because the corner case bug, whose probability of occurrence was once in a million, actually ended up being more frequent. Now, Intel isn't the only company that ever had a broken silicon, and since then they invested huge loads of money building state-of-the-art labs, and right now they do cutting-edge formal kind of issues that we catch these days by formal linting in hardware anyways. Meltdown, Spectre, Pac-Man, I could go on and on. A lot of these bugs are entirely down to hardware optimizations, speculative fetching, caching, all of these interesting areas where corner case bugs are going to actually drive you mad. But let's take a step back and come back to processors. So it is not just functional verification why processors is hard. So most of the world has been working, if you look at going from architecture to silicon, in a rather discrete manner rather than in a full continuous manner. So what I'm actually saying is that the verification approach needs to be holistic when you're looking at the architecture specification of a new bus protocol or a new architecture such as RISC-V. Makes the slide. So what I'm saying here is that you have to look at verification from all angles. These overlapping circles on the right-hand side of the slide are actually demonstrating what happens if you have a deadlock that may have resulted because you had an X issue in the design. What happens if you have a deadlock that is actually being caused by a power optimization? So all of these bugs and causalities are interconnected with each other, and it's not okay to just do one part and forget the others. So this Venn diagram was developed when I started finding bugs in 2 open source cores, where I have actually found all of these bugs as a result of verifying them architecturally. I have found issues with lockstep, with X, and I will be talking about some of these today. But if I couldn't cover all of them, you're welcome to look at our YouTube channel, where a lot of the videos talk about the details. And I'm happy to talk to you offline or later. So modern day processors are massively optimized. The kind of things that Tenstorrent is building, as Jim was telling today, 8 wide superscalar out of order cores. And all of them are, of course, going to have the basic optimizations, but also more fancy ones. So a lot is going on, and time to market is shrinking. You're not getting more weeks or months to verify your next chip because, hey, you want to leave your competitor out of the market. So why do bugs escape to silicon? And my answer is that it's because stimulus is the weakest link. Too many dependencies and scenarios to cover exhaustively. So conventional verification of microprocessors way back in 70s and 80s, a lot of this is relied heavily on architectural testing. And today we also use these compliance tests for architectural testing, unit level testing, or UVM randomized testing. So unit level testing is good for bring up testing. I think Neil alluded to this in the compliance bring up phase. And he said it is incomprehensive, so you need to do other things. Randomized testing, Lavanya alluded to this, saying, look, it can reveal corner case issues. But neither of those are exhaustive. And this is where formal actually shines a lot. So simulation alone, if you were only banking your buck and taping out your silicon just with simulation, right, you're going to be in the wrong list of famous companies. Actually constraining any particular instruction to be issued at any specific point or any specific number of times. We let the formal tool drive any number of instruction interleavings arbitrarily many times, how much cloud infrastructure you use. These numbers are astronomically big. I mean, there are not even atoms in the world or in the galaxy that if you do these numbers, those many simulation patterns or test cases you have to use, and not everybody is going to do exhaustive. People in simulation know this. So functional coverage is your gating criteria. But even for simple things that's complex, what happens if you have speculative branches? Forward jumps, backward jumps, page size jumps, page boundary jumps. What are you going to verify if you write a test targeting a specific scenario? So back-to-back memory operations, these are my favorite ones. Load store units, especially with L1 cache memory subsystems. When you have variants of loads and stores, bypasses, atomics, and cache coherency makes the whole lot more interesting. So when you have complex control and data dependencies, I mean, this is an example of a simple program. What if the second load was issued out of order with respect to the add instruction? What is going to happen? Now, if you were running test programs, you would consider different interleavings and combinations, and you can make these test cases very intelligent, and you can use automatic test pattern generation to make it even better. But look at this fragment of the program. Depending on whether or not the first branch is exercised, the second one may or may not get exercised. That allows add instruction to overtake both of these branches. For whatever reason it may actually be happening, you're going to get unpredictable results. So my question is, if you were worried about verification, interleaving, scenarios, Human beings cannot sit back and dream up of all possible scenarios and test sequences that you can write. It's not humanly possible. And that is why I was saying that you have to think a little different. So memory model, this is another favorite topic of mine, memory consistency. So this is a higher order logic maths looking axiom, which is one of the axioms from the RISC-V weak memory model specification. And I'm not asking you to go and learn HALL to be able to say something quite trivial, which is that if you do multiple stores followed by a load, then the load should actually pick up the last value of the store. Instead, what we will do in our world of formal is we would issue a load instruction, let's say for load word by word aligned, we would actually expect the result value to be the right one. And when we do this, we don't actually constrain any number of loads or stores to be happening in a specific format, or we do not prevent any other instructions from happening. So just the fact that you can get this property to prove would basically mean that no matter what happens, this load word aligned would always work correctly. Now, if we can do this, then you don't have to keep running these test programs forever. And this is the power of formal. So bugs and proofs. So here is the status report of some of the cores that we have looked at. We have more in the pipeline, but we're not ready to share this information. You will notice that some of these, IBEX 0 RISC-V and CV32 E40P, were verified by simulation, and CV32 E40P from Open Hardware was verified by formal and simulation. What is most interesting is, I'm not getting surprised when we pick up bugs in designs that were previously verified by simulation for the reasons I described. But what surprised me most was this WAR5, because this was previously verified using the RISC-V formal open, and I wasn't expecting to see any bugs. And I'll give you the long story short message that these bugs were missed because there is a bug in the RISC-V formal test bench. And when the designer was looking to build his design, he trusts the verification guy so much, so he basically copied what was in the RISC-V formal model into the design. And they were both incorrect in the same way. So all of these have been recorded on GitHub, and you can go and look at it. I'll tell you briefly the details. What we're really saying is that we have built this app called Formalizer, and it verifies the processor core for 64-bit, 32-bit. And you are not limited only to look at the core itself. You can actually go all the way to the full memory subsystem integration via your protocols. So we could type protocol checker, and we could help you find bugs in your AXI implementation or the core or the memory subsystem. So let's take a look at some of the bugs that we've picked up. So this is the most simple one. This is in 0 RISC-V. 0 RISC-V was already in silicon at the time I picked it up. And this is the load instruction, the property that I showed you earlier. We can't actually get that to work correctly on 0 RISC-V, and that's simply because by accident, they left a custom instruction reg load code sitting right underneath the load case statement. So as a result, the muxes were behaving incorrectly, and the load from memory instruction just wouldn't work correctly. And you can see it's only a 4-5 cycle trace. Now, this is a very interesting. After I had finished working on 0 RISC-V, the developers at Low Risk in Cambridge asked me to look at IBEX because they said they have literally just changed the regular expression namespace change, and 0 RISC-V is now called IBEX. Do you mind running your app again? So I said, yeah, sure. I started the app and went and started to boil the water in the kettle to have some tea. By the time the water was boiled, I had all of these bugs coming back in the Jasper Gold tool that I was running at the time. And it was a little surprising, and because, he just said it was a regular expression change of namespace. But they were working on this design. They were working on the control unit, and there was a real issue going on there. And the issue is that if you look at the bottom part of the slide, then you have the controller FSM state being in decoded state, and a debug request instruction arrives. And if that was to happen, then actually all a big deal. The design was under development, so you would expect designs to have bugs. The big deal is that this design was a delta from the other design where this bug doesn't exist. And when I actually found the bug, I found the reason for the bug, and it says we have to work on this FSM again and so on. The big deal is it takes 30 seconds to find this. And not just this, but in addition, prove that this behavior would only ever manifest if the controller FSM was in decoded state. So I kept digging, and in formal, I was able to prove that if the FSM states were either reset, boot set, or first fetch, the processor would continue to work correctly. So coming up with this kind of weird scenario thinking to see what if this was to happen along with 100 other variables and timing is not easy. So that's why I'm saying do more formal. So this is an interesting one. This is CV32E40P. So what is happening here is we have got an e-break instruction that's been issued for debug reason. What has happened is that there is a preceding store so by the way, the effect of the e-break is to make changes to the MCOS register. What has in fact happened is that the pending store, which is this instruction, is blocking the execution of e-break. So e-break is a privileged instruction. It should not be blocked by any user instruction. And the reason store is blocking it because I have blocked the return valid from memory deliberately as part of doing some understanding security type analysis of this core. So incidentally, it is only the load and the store instructions that would cause the e-break to be blocked. No other instruction would be able to do so. So I maintain that this is an issue, although the designer disagrees. We have carried out an extensive security analysis on a number of processors using what is called a CVSS score mechanism. And there's a DAC paper which you can go and look at. So we are able to characterize the intensity of these issues through vulnerability scores. So this is WAR5. The jump and link instruction doesn't raise trap. BLTU doesn't raise trap either. AUIPC. So this is a brilliant intern I had from Bangalore. She worked with me for 6 weeks. And she was able to use the app to find all these failures. So the div instruction doesn't work correctly. So I wasn't getting surprised anymore because we were seeing patterns. So this is a slightly newer development because we started looking at open source AXI protocol implementations in hardware. So this is a bug that we filed very recently. There is a deadlock in the Perl platform AXI implementation. And I think they have acknowledged this to be a bug and have assigned it for investigation. And what's happening here is that if the AW and W channels are busy, for whatever reason, for example, you may have a stream of continuous writes going on, then AR valid would wait forever for its AR ready. And there's no way to perform a read if the writes have a priority over read. It just happened to be the case. So this is what this waveform is showing, that AR ready can't actually go high. This is another interesting one where the basic AXI protocol on B valid and B response is not behaving correctly. The portion in the red is showing that the thing is changing. The yellow section shows that on the master side it is working correctly, but on the slave side it isn't. Presumably this has been going through some verification, I would imagine, but just bolting our system Verilog assertions onto a protocol checker and running them in formal would pick these up in a matter of seconds. So we have been able to prove that a lot of the other AXI protocol features do work correctly all the time on the Perl platform. So it's quite a nicely designed IP in my point of view, other than these two. Let's take a look at a memory subsystem. So this is a more interesting one, right? This is the kind of stuff that will get me up from bed in the night and get me going. So here is an example illustration. A processor is sending data to the memory. You have an MMU, you have a cache, and you have a way of tracking your cache misses in a miss buffer. So So the usual behavior that you expect, that if the data isn't available in the cache, you would expect to get it from the memory, update the cache correctly, line validation, invalidation would be working as you would expect. This is a bypass store, so it bypasses the caches and goes directly to the memory. So what is happening here is you have a load word, and this waveform shows it's all to the same address. You have a load word 8, it misses in the cache, and the request is sent out to the main memory where the value D1 is sitting, and the miss buffer now has an entry for load word. So what happens is all of this has happened, and the memory has now received you had a stored word. Now, remember, it doesn't have to be any specific number of cycles later. It could be any number of cycles later, or it could be the following cycle. We do not constrain this to be any specific one. So obviously, the store word request has reached the memory, and at some point, the value requested from the load, the responses have reached the processor, and the processor is expecting to see the value D1 being visible in the cache. But what happens meanwhile, because the store is a bypass, it goes and updates the memory to the value D2, and the responses are communicated back to the processor. Later on, you see the cache has been updated with the value D1 for address A, and memory has the value D2. So a subsequent load comes along for the same address, and it picks up a stale value because the store, which was the bypass, forgot to mark the cache line as invalid. So all it had to do was to not mark the cache line as valid. Now this is a very silly bug when I explain it in a way like I did in a talk like this. But imagine all possible permutation combinations of all variants of loads and stores interacting with all threads of the processor in a cache coherent system. This is going to ruin your silicon. So of course we can find bugs, right? I've shown you at least a few cases. But can we build exhaustive proofs, hey? Because people say formal doesn't actually always build exhaustive proofs. So the nice thing with our solution is that it works with all the formal tools in the market. So this is a snapshot of the IBEX and zero RISC-V cores. I tested this with all the 4 last year, and there was no real issue. When the cores get harder, bigger, you start using more tools, but then some tools don't produce results, some provide faster. This happens to be Cadence Jasper Gold on CV32E40P. As you can see, this is completely end-to-end with nothing being black boxed or cut pointed. The whole operation used to take a few hours, and the app itself takes a few seconds to get configured and run. Okay, so people said formal can only do small cores. So I said, fine, we'll try bigger ones. So this is CBA6 in order issue, out of order completion. And this is how the dashboard looks like for CBA6, at least some of the properties here shown in Cadence Jasper Gold. So the apps has got a lot of features. One of it is coverage analyzer, which allows you to probe deeper which combination of instruction sequences always work correctly, in addition to the fact that you've actually always proved that any arbitrary number of occurrences work correctly. We also built a debug tool called iRadar, which allows you to save an enormous amount of time not having to manually debug anything. And we've also made SURF, which is a scheduler and reporter for formal. So this is how the app works. We've taken the RISC-V ISA and turned this into a set of formal properties, which at the time of a configuration, based on the processor that you're using, can be configured with a setup file, and then the formalizer app's properties and the designer fed into a formal tool, and you either find failures or you find bugs using any tool you like. So in my world, there are no test cases to write, no manual checker to write, and no verification code unless you want to write code for custom instructions. And the beauty of this is that it exhaustively proves that all ISA instructions work as expected under all conditions, in addition to picking up microarchitectural issues. So there is a lot that you get for your money. What you normally do, and this is how we were running on the during the CV32E40P work, is every time the design would change, we'll grab the new design and come up and drive the app, and off it comes. I really didn't have to do any other thing. No make files, no nothing. But why should you trust us? Today, I would like you to look at this slide and take me for my word, but don't take me for my word if you like, and please challenge me offline or later. I will be happy. We do a number of things to actually establish that we haven't done a bad job at missing the bugs. So we start from the processor coverage. We look at assertion coverage metrics. And there's a very detailed video on YouTube that explains these in more detail. So you're welcome to take a look. We've spent a lot of time building techniques for over-constraint detection. We use vendor tools for making sure that we're not blocking any stimuli by accidentally writing an over-constraint. We're running checker coverage, mutation coverage. And we have built a scenario coverage as well so that you can collectively have a good feel of the overall environment and you can verify beyond doubt with Formalizer. So I know I'm running short on time, but I'll do this last section very quickly. So what is scenario coverage? So let's say I told you I verified with Formal and you don't trust me, and which is right. Verification is not about trust, but it's about proof, right? So you said, tell me whether the OR instruction works correctly. But I want you to show me that it works correctly under a specific disturbance, which is to drive a subtraction instruction 4 cycles after reset up to 2 times, and a cycle after you've driven the OR instruction in the pipe, issue an AND instruction, and then prove to me that the OR instruction works correctly regardless. So you just have to write me a spreadsheet entry, and we will take it from there, and we will generate all the assertions and covers, and you will end up getting waveforms like this. This specific one shows data forwarding working correctly for OR instruction. And this is a spreadsheet we used to analyze the CV32E40P, and that gave you a lot of different properties that could be run automatically. And once these properties have finished, then basically you get a dashboard that looks like this, and you can get the status of which properties have been covered, which properties have been proven, whether you had a bug or didn't have a bug, what formal engine was used by the specific formal tool. So we're trying to make it as easy as it could be and as fast as it could be. Bugs are a natural consequence of design. Bugs spotlight in the design would result in very expensive fixes, and as I showed you, catastrophic failures in some case. Formal does enable efficient bug hunting and exhaustive proofs right at the time of design bring up, and you could continue to do this all the way until you tape it out. My view is that architectural validation must employ Formal to build proofs of bug absence. And this can be used by everyone. There is no discrimination that only verification engineers can use. Architects, designers can use it. I mean, I've got high school children trying to use my app. They can use it too. They don't have to know Formal. I'm not saying it's an excuse and you shouldn't. They don't even have to debug. They can drive the tool, get the waveforms, and send it to the designer. So you can do all of this within the framework of Formal, and it integrates nicely with simulation. So I'm not saying don't use simulation. I'm saying use Formal as well as simulation. And find corner case bugs as well as exhaustive proofs. And I'm happy to take questions. Yes.
Thank you. Thank you, Ashish. Please raise your hand if you have any question.
Thank you so much for the talk. Just one question I had. When you say have formal verification, it's good in the pre-silicon phase, but let's say once the chip comes out, you have to validate the chip. So is there any scope in which you are able to generate the test cases? Because there's a concept called portable stimulus, which is the opposite of formal, where it generates more cases than the counter examples.
Yes. So I understood the question. The question is whether we can actually do post-silicon type analysis or at an SoC where we may not know exactly what this test case may be, and portable stimulus allows you to come up with test cases. So formal is test free. What does it mean? It means that human beings don't have to write a program to generate a specific combinations of sequences. So in the case that you are referring to, what we would write is the property, which should be an assert or a cover, and we would let the formal tool drive it to either prove that the bug exists and then prove that it doesn't once it's fixed, or it shows you a specific train, see a precise combination of signal values. So actually, there is no problem with formal going into post-silicon. Actually, as we speak, we have been helping some of our customers do exactly that. They have had bugs in post-silicon. Unfortunately, they were missed. We went back and wrote some test cases for them, and they were able to A, prove that they exist, and B, prove that the fix is done. To think about formal, you really have to come out of the test mindset. And this is why it is hard for people to do this transition, given how many people use test and simulation. It is very hard. And when I teach people in my training programs, the people who take the longest to learn formal are the ones with the most UVM experience. So the first 2 days is unlearn everything and then come back to this. So I say, forget everything you've learned for 2 days, believe me, and then you can come back and bring your knowledge back. So yeah, there's no manual test cases to write, right? So this is the biggest win for formal other than exhaustive proofs. Convinced, not convinced?
I'm convinced. Just that I just want to know. I mean, how do you test the chip once it is taped out?
So once it's taped out, well, what we test is Verilog or VHDL. So I'm assuming that still exists, so we can compile it and then run the. So everything I talked about is at RTL level. It can also be done at gate level, but there are not many commercial tools that allow you to do gate level. I think there are some proprietary ones, but not open tools. Yeah.
Sure, let me walk around. You don't want to? Okay. Got another question, right?
So can you give us an example of, for let's say, a 32-bit RISC-V, processor, a 4-stage in-order processor? Like how many properties were required to, and then how much time it took to exhaustively prove those, basically? And then the second question is the formal ISA configurable for the configurable RISC-V?
So it is
processor?
fully configurable.
Okay.
We don't need to know anything about your design details. You may have an in order, you may have an out of order. In terms of the number of properties, so on CV32E40P, we had about 5,500 assertions and about 20,000 covers. I think the overall suite is about 20 to 25,000 properties. Not all sets of properties are always executed because not all RISC-V features are always implemented. So then we start getting failures, so we have to disable the checks. So by and large, you can think of it as being a 30,000 property set, and those properties are run independent of each other. There is no dependency. You run them all in parallel, and each property is checking a specific instruction, but unconstrained in any other way. Sorry, I forgot to mention the time. So on CV32E40P, it was 2.5 hours from start to finish, using 4 licenses on a machine with 256 gigs of RAM. So it was not super cheap, but not super expensive either.